right? So we want to find all t's for which this limit is also 0. Okay, and this is given. Yeah, let's think. Let me also let's think. Mm-hmm. Mm-hmm. Okay, okay, that's good. So now let's see if others can build on this. I think this is crucial. Yeah, I didn't see this. Yeah, you have to just multiply divide by xn, right? Then what happens? Let's see. Yeah, so let's just give ourselves a minute. See what we can see. So nothing has changed. Remember, you can always multiply divide by this, and it doesn't change anything. So this is to everyone. So I mean, my point is, what t can you surely say that this t will work? So you can at least get that out of the way, and then focus on the non if there is any. Hmm. Okay, so you're saying that all t less than 0 is easy, less than equal to 0. Okay, does everybody see that? That when t is less than equal to 0, then it is just obviously, right? Because you can, it will come in the denominator. This will become log n to the power something positive, and so this is obviously 0. This is also 0. So this is 0. Okay, so we remove the easiest case first. Then what should be the next? Maybe we should look at t between 0 and 1. So yeah, what can we say about t between 0 and 1? Oh, so you're saying there's nothing special. Okay, so yeah, may not be. That's right. Yeah, that's fine, but still, there's no harm. So if you can reason this first clearly, then we can extend the reasoning and meaning. Yeah, yeah, you're right. They might not. I don't think. Yeah, there is any. But still, I don't know because log n square that might be, I don't know, dominating, and on square root of log n may not dominate. So I do not know. So here you can take a typical. It's always good to maybe just take like this and then take this and then work both of them out, and that should usually be will provide sufficient reason for it. And of course there is an xn. So what can we say about this quantity? At least can we say anything? If you can say something about this quantity, then it would be good. Square root of log n. Yes, that's right. Now that goes to 0. So that's always true, right? Because n is, I mean, if you want, you can just convert this whole problem into exponentials. You can do that as well, right? So then things will become more clear. Yeah, so you can reason this in other ways, but the way one can also do is you can just write it as an exponential, and then this would become square root of x by e to the power x. So this obviously goes to zero. That's the whole thing about exponentials. You prove it in any ways, and you can check the same thing happens here. So it's unless something is going wrong, this is a very easy question, right? So x square easy in the sense that it's surprisingly easy. So it means may not someone may expect that it is hard, but it seems very easy. Yeah, means I was also not getting it, and I tried for 5 minutes. But anyways, yeah, you see this becomes this, right? If you consider this as this, so this also goes to zero. Any polynomial, yeah. So this works, right? So this was, I think, ISI or CMI 2020, something like that, right? And the whole it's based on the idea that polynomial by exponential goes to zero. And I remember a few years back also they gave a problem in which the same idea was used, right? There was a polynomial and an exponential ratio, and they wanted to prove that it, I think that was a CMI question a few years back. And then this ISI question also is the same thing, I think, unless we are doing something, yeah, wrong. Seems correct. So is it true that then it works for all t, right? All t. Yeah, seems like it works for all t. For all t, in fact, yeah. So I'm just saying that this was the same thing was used in some previous EMI question, and they had two polynomials and one, and then this is in an indirect way. Okay, you can prove this by L'Hopital also, obviously. Okay, okay. So now let's get to one or two more serious questions, and then there is one more easy question which I want to do in the end if we have time. Okay, so this is now let's do this thing where people have the question. So I'll be doing this question about polynomials. There is a function which is from the collection of all polynomials. This is a nice question. Okay, let's see. I have been able to do part of it, at least till some part, I think. Yeah. So this is a function which takes in a polynomial and gives you out a polynomial. Okay, and these are very important functions in higher mathematics. Okay, like in this space of all polynomials, very interesting, important. Like derivative is one such thing, formal derivative is one such thing, and obviously there are easy things also. Anyways, so but some properties are given. Okay, and yeah, so f of 0 is 0. Yeah, f of 0 is 0. That's number one. I'm just writing it in short because you people have the question. And if you take the image, the degree of the image is not too much. That's all this is saying, right? The degree of the image cannot increase by more than one. Okay. So when I read the question, I also always try to frame it. So when you read a condition, you can immediately try to frame it in your own way. That may help you to think. Okay. Otherwise, it's sometimes just like staring at it, not really. Yeah. Unless something symbolically happens. And then there are two of them here. X. Okay, and the polynomials p minus fq. Okay, so it's a new type of question, I think. Uh, Polynomials p minus fq. So you see fq is also a polynomial, of course. And q minus fp. So this happens for all p and q. Okay, have the same. So here also there is a one thing as we focus on, same real roots. Okay, same real roots. And these, of course, can have non-real roots also, the elements in that Rx. Right. Same real roots, and again there is a thing, same set of real roots. So the multiplicities could be different. Yeah, all this is really the real roots part was has still I'm still not able to go through that. Why, like how to use? I think that's why I'm not able to complete the question. Set of real roots. Yeah, this is the thing. And now we want to find all such functions. So maybe some of you who have tried this, can say what you have done. Maybe at least some of it you can say if you've done a lot, so that we have an opening. Hmm. F is not a polynomial. F is something that takes a polynomial and gives you out a polynomial. But yeah, in that sense, it might be linear. Yes, because you see the degree doesn't increase, but it is not a polynomial. It is linear in some other sense, maybe. So you see, it's not a polynomial, it's an operator. It's something that takes a polynomial, so it may be the derivative function. Okay, f may be taking a polynomial px and giving you out p dash x. Though you can check that it doesn't satisfy this condition. It satisfies the first condition, and that's why I was making this guess. It's not a polynomial. It's a map, and it will turn out in the end that it's a linear map between these two vector spaces. Yeah, but that is not useful even. Couldn't use it to solve the thing. So I don't. That interpretation is not used. At least I don't know how to use it. But I suppose the problem was made something using that kind of thing. Yeah, but some ring theory would be used here to make the problem because of the root thing. But anyways, that's not useful. So f is not a polynomial, okay? F is something that takes input of polynomial and gives output of polynomial. So you can guess f based on that. What is f doing? What are the obvious players? What are the obvious candidates, I should say? It's really the novelty of the question, new kind of question. That's really the whole thing. Otherwise, you people would start doing a lot of things here. If once you start seeing this as more questions. What are the obvious candidates? See, this is an Olympiad question, right? It's a contest type of question, right? So it should have a clean answer. What are the obvious candidates? So it's a polynomial on the space of polynomials. You can say that, where the polynomials are variables, and something like that, if you want to say. But yeah. So any obvious candidates that want to say? Is certainly the identity function, right? Certainly the identity function works, isn't it? I mean, something that takes a polynomial p and gives you out the same polynomial p. F of px would be px. So just writing p here because polynomials here are like elements. Any other candidates that people can think of? Fp equal to minus p, does that work? Let's see. It's so if you say Fp equal to minus p, then it certainly satisfies this. Right? Does it satisfy this? So let's see. Then what does it become? Minus p and no, so it's minus q, right? So fq will be minus q, so minus of minus. Yes, exactly. I mean, they become exactly the same. So it's really saying that we'll see. I think if so, usually this should be the only answer then, but let's see. I think so. These two are our obvious candidates. Now, what should I mean? If I was, what would I do? Is just see if fp equal to kp works. Some other k. This will say a lot of things. If it does, then some doesn't, then the technique. Okay. So let's check this. Does this work? Can anybody try to check? Should be easy to check here. Here you can check. You can pick your favorite polynomials and you can check. So this is a question mark. I want people to just check this independent. Maybe just try to do it on your own because you have to get a feel of this question. Otherwise, just knowing the solution will not be, if we do it, may not be useful. So how do you check this? Just take some polynomials, take px equal to x, and maybe take qx as something different. Okay. Take qx as x x, yeah, just anything x square plus 1 maybe. Okay, and then c, we have px minus f of this. So f of this would be k. So question is some other k works or not. For the time being, let's just take k to be k, and if it looks too hard, then we'll change it to something 2 or something. Let's see. And then q minus fp. So again kp. So see, these are the natural things that one should do maybe. Okay, problem. So do these have the same real roots? How? I- In, okay, okay, right, right, right. That's good. That's good. And so you, that's, and so it has to be right. That's good. So you took a better. This is a better example. Yeah. So since the point is that because this has to happen for all p and q, you should vary the p and q. Treat it like a functional equation. It's a functional. It's a functional condition. Okay. Right. All right. So this has to be, if this is the case, then this is the only situation. Yes. Mhm. Right. No, but you do not have to check that. Think about that. Even what I did is you not necessary. What Rupsa has done is much easier. You have to just check for a pair of polynomials. See, this must hold for all polynomials. This condition must hold for all polynomials p and q, p minus fq and q minus fp should have the same real roots. So if you can find one pair of polynomials for which k is forced to be 1 or minus 1, that's it. Okay. You have to just find one counter example, no? So for one thing, so you make one substitution and you can find extract some information. So I made one substitution, px equals to x and qx equal to x plus 1, and you extract that k should be this. That's it, because k has to satisfy there in that small situation. So you don't have to try for higher things. That's the thing. Treat it like, I mean, just vary the p and the q over. So this is the moral, this is what I am learning from this, right? That you change the p and the q and you get a lot of things. So this is, if there are simple answers, then this is the only possibility. And I do not think that it will be some like p equals to p squared. That certainly is not going to happen. I don't think that happens. Otherwise the degree will blow up at some point, something like that. Okay. Right. So what can we do? But we have learned this thing, that substitute, just like what we do in functional equations, right? Substitute different special or different or special. Yeah. Yeah. Mm-hmm. 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 Yeah, see, so these should have the same, yeah, same set of prime divisors for all p and q, right? So this implies that in particular, for p equal to take something 6 and q equal to whatever 4, these two should have the same prime divisors. right? So can't you extract something about k from here, right? This will be this, and if this is k times 4, and then you have this q 4 minus again k times 6, then these two should have the same prime divisors. So from here you can say something about k, right? These two should have the same prime divisor. This will, I mean, I'm not saying you can say something conclusive, but you can say something about here, from here, about k, and that thing that you can say here must be true, in the sense that k must satisfy that, because for all p and q this one must be satisfied. And so yeah, you can substitute anything and the condition must be satisfied. That's what it means. Yeah. So 4k minus 6 and 6k minus 4 should have the same prime divisors, and so whatever you can say from k from here will be true generally. And here when we took two polynomials, we were able to say that it has to be 1 for those pair, and so it must always be 1. Is it okay? Okay, okay, yeah, okay. I mean, see, here I'm not able to say anything, because yeah, here I'm not able to say about anything about k. Or maybe we can say, if we just try to take some other numbers, maybe we can say. So I don't know if everyone has to try that. But yeah, if once you take more numbers or choose them more wisely, you will be able to say some things. Okay, some divisors and so on, maybe. Or maybe, yeah, I don't know. This will be a more complicated question, because prime divisors are, degree is a much easier thing, right? Degrees and roots are just, yeah. Anyways, like, okay. So the idea is that we must try to substitute different kinds of values. Okay, so let's introduce this technique. It's, I think, is a good handy bookkeeping technique. You just call this statement S. Okay, and this statement is true for all P and Q. So we can call this statement. It's just a good bookkeeping technique. Okay, this is true for S, P comma Q. Let this statement be P comma Q. Well, not this, but the whole thing, of course. This. So you see, like a functional equation, not equation, but function statements, function statements. So now, what p's and q's should we take to extract more information from here? What can be substituted in place of p and q? So remember, these are our uh, only. This is our kind of a soft claim. So what are the natural things to substitute here? Obviously you should substitute p equal to q and things like that, isn't it? I mean, what else? When you have equation x equal to y, x equal to minus y, things like that, you substitute, isn't it? That's the only way to get rolling. So we substitute, uh, let's substitute p equal to q only and see. So substitute p equal to q, get this. What do you get here? Hmm. Yeah, that's not useful. That's not useful, right. Sorry, that's not useful. So what should we substitute then? P minus p, is that useful? Minus f of p, no, that will not be useful. Or let's minus p minus f of p. So these two things should have the same roots, should have the same real roots, right? They should have the same real roots. So what does that mean? So it means that, does it mean anything? So those should also be the roots of, I mean, if you add these two, right? minus fp. So anything that's a root of this is also a root of this. Right, so I've just added these two things. So any real root of this and any real root of this, they have the same real roots. So those will also be the real roots of minus fp if you add them. And then if you subtract them, then they are also the roots of p. So, right? So any real root of p minus fp, so any real root of p minus fp is also a root, common root of minus fp and p. Yeah, at least we are able to say this much. But this doesn't say that p and fp have the same real roots, right? This just are fp and fp. Doesn't say that they are the same root, but they have common roots, and they are common with this. Mm. Right, that's all it says. So not much. I don't see anything interesting. What other substitution can we make? So now you should look at, maybe like you should try to make substitutions which would kind of make one of them zero. Like that's another obvious thing to think, right? Substitute like that. So how do you substitute to make one of the items zero? Right. What should you substitute to do that? So obviously, you should try to substitute maybe q um, p equal to fq, or q equal to fp is more no. Yeah. So you do p and fp, right? This is again a natural thing to substitute because you want to make one of the things zero. So you do p minus f. Okay, but this becomes f of p, right? But no problem, yeah. Then this becomes fp minus p, 0. So what can we say from here? What can we say from here? Okay, that looks it. Okay, someone else was also saying something with this statement. X to the power n. No, it cannot be x to the. Oh, it can be x to the power n also. Yeah, that's all right. Okay. So no, not just x to the power n, right? No, that's, you don't need that, right? Because look, this is zero. It has all real roots. Everything is a real root of this, so it has to. This has to be zero only. Yeah, this has to be zero only, I think. Yeah, that's it. But that's, it was good you said that. Actually, it means that thinking across the thing. Yeah, that's good. Actively, right? So this, from here we conclude. So now I just write f of p equal to p, which want to create space. This is already a big opener, right? This is, I mean, if you see this, this is an idempotent, right? Idempotents are, this is, okay, sorry, this is not idempotent. This is a square. This is like f square is equal to identity. Sorry, certainly this bullshit. F square is equal to identity. So what can we say about f from here? Right. So this means that f is injective and surjective, right? I mean, so f is a function that takes a polynomial and gives out a polynomial, right? But it has an inverse. It has self inverse, right? fp goes back to p, and so then this will like enforce this even more, right? That especially this one. I mean, obviously the first one is there, but this one is just enforced from here. Right? It has to be minus p, just a order 2 thing. So this means that f is bijective, at least. We can try to use that. Of course, we can't say monotonic and all from here because it's taking a polynomial. So doesn't make sense. Okay, so this seems to have taken us somewhere. But what else can we say now? Huh? Huh? Right. Ah, it's a polynomial. Yeah. Okay. So it's bijective. We have not yet been able to use the degree condition, right? What can we say with that using the degree condition? So you see, the degree of fp cannot be too big than p, and the degree of f of p cannot be too big than f of p. But then f of p is p, so this should give us some bound, some further lower bound, I think, or no? Yeah. Uh, yeah, it should give a further lower bound. So let's try to explore the connection of this with this, right? Because you can feel it already, I think. So I'll remove this one. So this idea of mine was not very useful. At least, I don't know. Let's see. Yeah. Okay. Let me see. Run my argument again. Might be some fault. So I've substituted p equal. I've substituted q equal to fp and p equal to p. So when you substitute q equal to fp, you get this, right? And in the second one, q is equal to fp and p is equal to p, so you get this. This is 0, right? Now 0 and these are polynomials. Okay, maybe I should have written px, polynomials. And they have the same real roots. It's good to go over, it's not a problem. This and 0 have same real roots. What does that mean? It means that any number is a root of this. I mean, just this is some gx, maybe gs, gx, right? Now think, this has every number as a real root. Every real number as a real root, as a root, right? Because 0 has everything as a root. So because polynomial gx has everything as a root, it must be 0 polynomial, right? Yeah, that is easy. You can show that. Right. It's good because this is a type of question. These are not numbers but polynomials. Polynomials. Yeah. Yes. Hmm. Sorry, f to be a permutation. Hmm. Hmm. Wait, what happened? This should be alpha 1 to the beta 1, right? Oh, those are these are multiplicities. Sorry. Okay, so these are that's an interesting way to see it. Multiplication, uh, multiplication, multiplicity of roots of px. Okay, then what you're saying? Uh, Okay, everything else is the same. Hmm. Okay, no, but okay, if this kind, so this is again a very interesting candidate. But what more can you say? It's a candidate certainly because it is swapping. No, but you see, problem is, yeah, say no, no. But the problem is that all that is fine. But before that, there is a fundamental problem which is usually overlooked in certain part of in mathematics. Is that is this a well-defined thing, right? Which two roots are you going to swap? That is the question, right? Which two roots? No, no, no. But one and two means what? Beta one and beta two. That is not well defined, right? So it is like, yeah, for some polynomials, if you swap beta one, sorry. Hmm. Yeah, at least in the highest. Yeah, that can be done. Okay, okay. Uh, 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 uh. Sigma, sorry, sigma is equal to. Yeah, yeah. So yeah, sigma square is identity, right? So if sigma takes I to j and this means it takes I to j and doesn't do anything to anything else. Yeah, then sigma square is identity, obviously, because yeah. No, no, that's fine. But then the well-definedness was a problem. But then the proposal here is that if you swap the least, or you can just take the swap the two least roots, that will not make much difference. But if you swap the two least roots of a polynomial, then that is a well-defined operation. But and this will be preserved. Yeah, but then will this be preserved? Yeah, this will be preserved, right? No, 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 no. It will not be preserved. That is a problem. No, it will not be preserved because I mean, when you take that common, the rest of the polynomial can have new real roots. So my point is like this: if you take, yeah, that will not be preserved, and all this will actually tell you that there is actually no answer other than this too. I think, but let's take it. If you take, let's not take any multiplicity. Doesn't matter. Let's just take this minus, or we should take some other things. Otherwise, yeah, I think we should take other things. This my point is this, that if you take the real roots like this, and if you are mm, what is the point? Yes, FQ, it is, this is FQ. So no, no, actually there is no reason for this to hold, right? Yeah, there's no reason for it to hold. Yeah, that's the problem. So what am I even doing? You just take any example, it will not work. Yeah, mean that there's no reason for it to hold. It was just set from here. So no, no, that, yeah, you can just check for any point or pair of polynomials, it will not hold. So this doesn't work. But still, it's a maybe good thought. Anyways, okay. So F is, yeah. So I was saying that we should explore the connection between this and this. Okay. So has any people have done it? So let's see. So we have this thing that degree of FP is not much bigger. It's at most 1 plus degree of P. But then if you apply the same thing, then what do you get? That, uh, one second. I was thinking something in the middle. Yeah. Anyways, so then you can apply the same thing for f of p, and what are you going to get? You're going to get degree of f of p. Is that right? Minus 1 is bound. But then you get interesting. This is what I was saying. This is like going closer to p equal to minus p. And yeah, so this. So you see, degree of fp is either equal to degree of p, which that's what we want to show. It's either 1 plus degree of p or 1 minus degree of p. Okay. So let's basically there are two cases. Okay, there are not three cases, only two cases in fact, right? The other case you can see it's just similar. The degree of p is either equal to degree of fp. Okay, let's hope this is what happens. Okay? And the other is degree of fp is 1 plus. The minus 1 is not very interesting. Let me just think about why it's not, but I'm getting a feeling it's not. It's similar to this. Yeah, see, because if it's 1 less, then you can just change the roles of P and FP and you'll get to this case. And you can change the roles of P and FP, right? Because of this equation. It does not really matter. You can think about that. Yeah. So we'll just take these two cases and work. These two are enough. So this equation is useful, I think. Yeah. So now what? See, yeah. Let's see. And we have also not used f of 0 equal to 0 yet. That's a very use. Mm-hmm. P minus Fp and these two have the same real roots. You don't get q minus f of q. How do you get q minus f of q? If you add them, then you don't get q minus f of q. Why do you get q minus f? Where the p will still be there, no? Plus p minus f of p. Yeah. No. No, because why is it linear or constant? Yeah, but then so if you say the degree of p and fp is same, then why should this p minus fp? Why should this be constant? Which inequality? This, yeah. Your degree is less than 1, but no. But no, I mean the degree is the difference in the degree is less than 1. That That doesn't mean that the degree of the difference is less than. Yeah. Right. Let's take see the first this condition. If we have this condition, then what can we say? Yeah. If we have this condition, then what can we say? Yeah. Let's first work with the easier condition, right? What does it allow us to say? Can we say that? So we have f is bijective. So it takes in p and gives you an fp. Hmm. I think we should make some more substitutions to get a. What substitution can I make? Hmm. Yeah. What substitution can I make from here? If I assume this only, that this case seems easier. See, the point is that look, what do we want to show? We want to show that these two and that P and FP have the same real roots, right? I mean, we can even write that as a claim. Because we know that that should be true, right? P and FP have same set of real roots. Same real roots. Can we prove this claim? I think this is the step. If we can show this, then we are done. We'll get to FP equal to KP, and well, the multiplicity problem will still be there, but yeah, but at least let's show this. Let's assume there are no multiplicities and so on. Can we then do this? Yeah. Hmm? Mm-hmm. Right. No. Ah, right. Yeah, right. Fantastic. Right. So it implies that f of p of alpha, f of 0 is 0. Yeah, that's what the thing was. Right? This is the cool thing. This is what we were not getting. Right. Nice. Okay. So we have shown in this direction. And can you just show in the other direction also? Maybe it's not needed if we assume that they have distinct roots, but yeah, we can do it in the other direction as p of alpha, right? Yeah. I mean, if fp has alpha as a root, then you can just take f again and you get p. So yeah, so they have the same real roots. Okay, you can just please work out the details. This is a big, it's a sort of seems to be a lengthy question, so work out some details. But yeah, so we have proved that they have the same real roots. Yeah, it was just very simple. Thinking I was stuck on this substitution. Yeah, just put the root and see. That was simple. Sorry. So they have the same real roots. Hmm. Right. So if P and FP, so if P has distinct real roots, if P has distinct real roots, right, then P is equal to FP, or like K times FP, right? Because if P has distinct real roots, then everything is same, and FP's degree is they have the same everything, right? Same degrees. But the problem happens when there are multiplicities, right? Right. So we know the degree is same, but the degree is same doesn't mean the multiplicities have to be same. That's right. Don't know. Okay, I think this is so. This implies that FP equal to plus minus P. Good. Okay, can we then eliminate this case? Should try to eliminate this case, right? Yeah, so claim this is not possible because I mean we know deep down that this should be the only answer. I think so. The degree cannot actually it cannot increase, right? So even if the degree increases, the real roots, right? FP has even degree, odd even. Uh-huh. No. That oh yeah. Okay, sorry. Go on. Yes. But the multiplicities might be a problem, right? That is the thing. You are right. If yeah, I mean any complex. Yes, yeah. Any complex root will always come with even. It will always have even contribution. Even if it has multiplicity, it will have even contribution. There's no problem there. The only problem is with the real root come multiplicities because we have real polynomials. So the real roots don't have much restrictions because it's real only. Polynomials is base is also real. So yeah, so see, we are almost done. We are almost done, except when they have multiple roots. And multiple roots are always a problem. I mean, I don't think any way to understand multiple roots in analytic algebra. It's always you have to take a derivative and understand multiple roots. But I don't know how derivatives will work out here. But can we eliminate this in a different way because we have so many possibilities here? So what I was thinking of, if you take a case like if degree of P is odd and degree of FP is even, then maybe we can, shift FP. So if degree P is odd, see we have made a lot of simplifications, but still we are stuck here. P is odd and degree of FP is even. So this FP is then an even degree polynomial, right? So then where was this expression? There was the expression, right? PFP minus P and P minus FP. This is an even degree polynomial and this is an odd degree polynomial. So this must have real roots. And this one, can we make some smarter substitution so that it doesn't have real roots? Yeah, something like that. Yeah, can we make some sort of a smarter substitution so that it doesn't have real roots? Because see, an even degree polynomial always has a minima, right? Whenever you're looking at even degree polynomial, you always have a minima. So you can always shift it, right? You can always shift it so that it doesn't have real roots. Shift it. It's like this. It will always have a minima. That's just. I mean, assuming the leading coefficient is positive, all that you can assume it's can multiply by -1 and so on. You can always shift it up. So how do you shift it up here in this? Meaning that if we just change the constant term, right? Uh, Don't know. How do you change the constant term? Because if you go to change something here, oh no, but you can just change, you can just multiply some big numbers here, right? 10 to the power 10, or meaning that you can just increase this or decrease this. That will increase or decrease the constant term, right? That will increase or decrease the constant term. And but no, but it's also changing the entire polynomial, right? The polynomial is also changing because fp has a degree. Mm, so then, yeah, I mean, we can just take this to be constant, isn't it? We don't have to. That's the problem. We are just in the same substitution, right? We take p and we can just take q to be 1, right? Then you have p minus f of q, but this will just be degree 2, a degree 1 polynomial, right? At most degree 1 polynomial, so some linear polynomial or constant polynomial plus some constant minus f of p, some or same constant 1 minus f of p. Right, here we can always do a manipulation, right? We can always, instead of 1, we can take a big number or something, and then this will not have real roots, right? Yeah, you can take q to be a constant and then it will not have real roots, and then that's a problem because this has real roots and this doesn't have. This will always have real roots because this will remain odd degree, p is odd. And you can work out the other direction also. Just try to do it on your own. It's similar because p equal to f of p is. But is this argument clear? Um, okay, we're just making different substitutions to serve our purpose. But here's the thing: a lot of backtracking has to be done. You have to make strong claims also. You have to make bold claims to be able to prove them. Otherwise, you'll not move in a way that. Okay, yeah. So this is not possible. Right? So this is not possible. Degree of p is equal to degree of fp. Now, how do we get rid of the multiple roots? I do not know. Um, degree is the same, but the problem is that if you have x minus 1, if p is x minus 1 cube and x minus 2 square, then f of p has the same roots. So we don't have to worry about the complex roots. So I'm writing that. This could be 2 and this could be 3. So in this case, this condition is satisfied. P has distinct real roots. I mean, we have learned a lot of things in the process, but we have not completed the question yet. Okay, yeah. I mean, all these techniques are all there for substitutions and so on. But yeah, yes. Not necessary. I mean, see, for some polynomials it may work, right? You can't say. I mean, okay, we can take something more complicated. That's not the point. Yes. No. But I mean, it may work for this polynomial. I'm not saying. It's the transformation may be such that it ends up permuting. See, it's like f was not intending to permute, but it may end up permuting for this case. See, yeah, it means polynomial is not identically 0, but it may end up being 0 for the roots. It's like that. That's not. That's just. I'm just trying to see an example in front of me. That's why. Otherwise, you can take a more complicated example and a more complicated distribution of the multiplicities and so on. But the degree is remaining the same. But yeah, but you're right. I mean, it kind of says that this swapping will never work. Like not even for any polynomial. That's the whole point. Yeah. That is kind of like like that. So we have to introduce new roots. There was this P minus Q and FP minus FQ, right? That's another type of substitution that is made usually. That is, if you put P minus Q, how do you get this? You get this by putting P comma FQ. That's a good expression. You get P minus Q, and here you get FQ minus FP. These are always special things. So these have common, I mean, these two have the same roots. Okay, these two have the same roots. All right. That's interesting. These two have the same roots. I mean, we kind of know, right, that this divides this, but MNF is a polynomial, not in this case. That's another substitution. And so we have P and FP. If FP has some root which P does not have, if FP has some root that P does not have, right, then if I bring in an auxiliary polynomial Q, I bring in an auxiliary polynomial Q where Q has distinct roots. Okay, so let's say why I'm taking Q as distinct roots, so that this becomes K times or becomes minus Q. Yeah. So if say Q has distinct roots, okay, so if Q has distinct roots, then the expression would become minus Q minus FP or plus FP, something like that. Right. So then these two, so whatever roots is there in P minus Q, that is also there in this, and then that will also be there in the difference. Right. If alpha is a root of P minus Q, we say it's in the variety of P minus Q in algebraic geometry. But here, if alpha, right, so we can just say if P minus Q alpha 0 and this of alpha is 0, then that will produce a root if you take the difference, right? And the difference is interest, or the difference, yeah. Then that will produce a root for the difference, and the difference will be Fp plus P. Right? Fp plus P will also have alpha as a root, right? If you take the difference. Right. Yeah, but the problem is that, yeah, someone has messaged. Problem is that this cannot happen because you cannot keep getting arbitrary roots, I think. Huh. Yes, yes. Yeah, we will just also end now in 2 minutes. No, this is not obvious because see, P minus Q has a new root. See, P is a fixed polynomial, right? And you are so P is a graph like this, right? You are kind of subtracting it with another graph so that now it has, now P minus Q may have new roots. So this is P, this is Q, and P minus Q may have new roots, which none of P and Q had. And you can always create these kind of situations, right? You can, because I mean, you're like translating P by an arbitrary polynomial, so you're bound to get new roots, right? So alpha is a completely new entity. You see? Yes. So my point is that I am trying to show, so I think now you can frame it better looking back, and then I'll say the whole thing clearly. The thing is that, see, I'm trying to prove that Fp minus P or Fp plus P is a zero polynomial. I'm trying to show that Fp plus P can have arbitrary roots. It can sort of have any random root. Not everything, but many random roots. So to do this, I am trying to use another polynomial Q. Okay, trying to use another polynomial Q, and what this polynomial Q is doing is that it's bringing a new root for P minus Q. Okay, so, and this can be done. This is not hard, because see, P is there, right? And choose Q so that P minus Q has a new root. Has a new, I mean, new means enough real numbers, so you can always do new root alpha. This you can always do. I think you can even choose Q to be constant, and just choose it to be a constant, right? Yeah, just choose it to be a constant. Yeah, that's good enough, right? Just choose it to be a constant, and it just comes down a little bit like this and just gets a new root. Yeah, so you just choose it to be a constant, so just shifting P here and there a little bit. Okay, so just actually take, let's see if it works like this. Okay, choose epsilon such that P minus epsilon has a new root. All right, now, yeah, now certainly we know that epsilon maps to epsilon or minus epsilon, right? So P minus epsilon has a new root alpha. Okay, but then if you put it here in f of q, f of epsilon, that is, let's say it's minus epsilon for a second, and then we have f of p, this should also have alpha as a root. That's the strange condition. This is a very strange condition, and that's why it's such a strange and unnatural condition that you don't get any answers other than the trivial answers. Okay, that is, I think, what's lying underneath the thing. Yeah. So you see, this is the thing, and now you can subtract them, or yeah, subtract them, get rid of the alpha. Then what do you get? You get that P plus f of P has a root like this. Epsilon was enough, I think. Yeah. I've just taken P. You don't even need a new graph. Just take P and shift it a little bit so that it has a new root it never saw before. You can always do that. Hmm? No. So that's what we're trying to contradict, right? That's what we are. I mean, assume it's not. Assume FP is not minus, but then we are done, right? If FP is minus P. Right. So let's say FP is not plus minus, not P, not minus P. Okay, then from here we are getting that FP should be minus P, because it has arbitrary roots, right? Alpha is created arbitrarily, right? You can create another alpha like this by shifting epsilon 1, epsilon 2 gently. Okay, so because you're creating arbitrary roots, P plus FP is equal to 0, so must have FP must be equal to minus P. And the other case is in which f of epsilon is equal to epsilon, then it's like this, then you'll get Fp is equal to P, something like that. I mean, you can do that a little bit. Okay, try to write it now. Okay, try to write it, maybe if you want to, and yeah, we'll discuss. I did plan to discuss the other questions also, but yeah, it's no. I mean, that's the way we should do, because so you learn otherwise. Okay, then that's it. Tomorrow morning also I'm taking a, yeah. Yes, say. No, we don't have to prove it. We don't have to prove it because look, there are two cases, right? Either FP is equal to P or FP is equal to minus P, right? If none of them happens, then it's a contradiction. Okay. So see, let me if you write want to I'm saying that when you write it, you will realize these things. If it is not P or minus P, right? And here, what kind of equations can you get? You can get only this kind of equation, right? This one can be minus also, right? So if none of this is true, then it's a contradiction. So if this is happening for infinitely many alphas, then one of them must happen for infinitely many alphas, right? P of f of p or p of f of minus p. One of this, both might happen, but one of this will happen for infinitely many alphas, and that will imply that that is an identity. That part is an identity. Okay. So yeah, you'll get it's either f of p or equal to f of p is equal to p or f or minus p. You will get one of them. You cannot conclusively say from here that it's p or minus p. Okay, I'm not saying that. This was just the case in which I took epsilon f of epsilon to be epsilon. Okay, right. Try to write it. You will see that I may have even made some mistakes in the process. If you write it, then only you can think clearly because maybe yeah. Okay. Yeah. Yes, so that was based on yeah. So if you have so that was a shifting argument, right? So if we have f of p, if its degree is 1 plus degree of p, right, and we can take p is even. So the underlying thing here is that we have those things, f of p minus q and q minus f of p must have the same roots. So if one of them is even, one of them is odd, if p is even degree, at that time I think I took odd degree, but let's take like this, p is even degree and f of p is odd degree, right? Then you can look at p minus q and a p minus f of q, and you can look at q minus f of p. Now you can choose your q conveniently. So the idea is that I want this to be an even degree polynomial. This is an odd degree polynomial, and this is even, right? The idea is that now I'll choose my q conveniently so that this has no real roots. You can do that. You can choose q to be a constant, it becomes a degree 1 polynomial, then you can change the thing and so on. You can make this have no roots, but this will always have real roots because this will be an even degree polynomial. You can choose q to be linear and so on. So you can do it. Now, yes, there then you can say that what happens when p itself is linear. That case I have not done. Then you can do it on try to do it on your own. That means you can do it. Yeah. F is linear. I've not done, but yeah, you can do it. Something like that. Little nuances are there. See, those will only be clear when you write it. Such a problem, yeah, because is okay. So that's it. And as I was saying, tomorrow I've sent some problem set again, which I'll be discussing tomorrow morning 7:30. It's just about enumerating walks and so on. It's an good topic, interesting topic. If wants to attend, you can attend. Yeah, that's it. Thank you.